diagonal matrices are actually very convenient. They are very easy to understand. And for instance, if you have a diagonal matrix, its eigenvalues are the diagonal elements and so on. There's so many nice properties that diagonal matrices have. And so in general, we want to know if a given matrix A is similar to a diagonal matrix. Okay, that is to say that the matrix A, it belongs to a certain equivalence class, and does this equivalence class contain any diagonal matrix in it? Okay, so that is the following definition. Is diagonalizable if it is similar to a diagonal matrix. So when is a matrix diagonalizable? So we have the following result. Is diagonalizable if and only if it has n linearly independent eigenvectors. Okay, so that is the requirement, that it must have n linearly independent eigenvectors. And we've already seen that if a matrix has distinct eigenvalues, then the corresponding eigenvectors will be linearly independent. And so any matrix that has n distinct eigenvalues will necessarily be diagonalizable. Of course, a matrix could have repeated eigenvalues and still be diagonalizable, and the identity matrix um, is an immediate example. All its eigenvalues are equal to 1. It has n repeated eigenvalues and it's already diagonal, so it is diagonalizable. And in this case, you can also see that any non-singular S is such that if I do S inverse times the identity times S gives me a diagonal matrix. So the matrix S that transforms the identity matrix to a diagonal matrix can be any non-singular matrix S. So that also shows you that this matrix S that defines the similarity transform connecting A and B to matrices, it need not be unique. Okay, so let's just see how this is proved. Um, so if there are n independent, linearly independent eigenvectors x1 through xn, then let the matrix S just be a stacking of these vectors. I'll not write it with commas. X1 stacked with x2, xn. So this is an n cross n matrix. We'll show that this matrix works. Okay, it will reduce A to a diagonal matrix. So all we do is we consider S inverse AS, which is equal to S inverse times A times this matrix x1 through xn. And this matrix, so if I expand this product, I will get S inverse. The first column of the product will be AX1. The second column will be AX2, AXN. And because these are eigenvectors of this matrix A, this AX1 is some lambda 1 x1 S inverse times lambda 1 x1 lambda 2 x2 up to lambda n xn. And if I consider a diagonal matrix with lambda 1 through lambda n as its diagonal entries, then I can write this as S inverse times x1 xn times this matrix lambda, where lambda equals, it's a diagonal matrix. Okay, this is just rewriting this product here. But then this matrix is just S, and so I have S inverse S, which is the identity matrix, which is equal to lambda. So we've shown that the matrix actually gets diagonalized. So what this shows is that if there are n linearly independent eigenvectors, then the matrix A is diagonalizable. By a similarity transform, I've reduced A to a diagonal matrix. Since it's an if and only if condition, I need to show the converse also. So if what we need to show is that if A is diagonalizable, then it must have n linearly independent eigenvectors. So if there exists an S such that S inverse A S equals lambda, where lambda is some diagonal matrix, then it means that A S equals S lambda. I'm just pre-multiplying by S. So this, just if I write out what this means in words, this means that A times the ith column of S is equal to, but lambda is a diagonal matrix, and so that will be, so the ith column of, so this will be the ith column of AS. So A times the ith column of S is equal to the ith diagonal entry of lambda times the ith column of S, which means that the ith column of S is the eigenvector of A associated with the ith diagonal entry of lambda as eigenvalue. Okay, so basically what this means is that the columns of S are essentially eigenvectors of this matrix A, and the diagonal entries of lambda are the eigenvalues of this matrix A. And of course, since by definition, if A is similar to a diagonal matrix, this S is a non-singular matrix. So since S is non-singular, there are, or A has n linearly independent eigenvectors. So that completes the proof. So basically this result that A is diagonalizable if and only if it has n linearly independent eigenvectors. So in principle, this is a way to diagonalize a matrix if it is indeed diagonalizable. So all you need to do is to find eigenvalues and eigenvectors of the matrix A, and then you check whether the eigenvectors are linearly independent, and if there are n linearly independent eigenvectors, then you can just stack those eigenvectors together, and that gives you the matrix S, which is a diagonalizing similarity matrix. Okay, so this is one way to find how to diagonalize a matrix A. So again, coming back to our previous example, this matrix 0, 1, 0, 0 is not diagonalizable. Okay, what it means is that it does not have two linearly independent eigenvectors. So, I mean, if this was actually diagonalizable, then there must be a matrix S such that S inverse times 0, 1, 0, 0 times S is equal to a diagonal matrix containing the eigenvalues, which is the all zero matrix, because both its eigenvalues are 0. But then this implies that if I pre and post multiply by S and S inverse, it means that 0, 1, 0, 0 must be equal to with 0, 0, 0, 0, which is not possible. Okay, so this matrix is not diagonalizable, and in fact, um, this matrix has only one eigenvector corresponding to lambda equal to 0, which is the vector 1 0. So if I multiply this matrix by 1 0, I will get 0 0. So that is so 1 0 times this matrix is equal to 0 times 1 0, and so 1 0 is an eigenvector of this matrix corresponding to lambda equal to 0, and I cannot find any other linearly independent eigenvector of this matrix A. So we see that the number of linearly independent um, eigenvectors of a matrix that you can find corresponding to an eigenvalue can be less than the multiplicity of the eigenvalue. Okay, the multiplicity of the eigenvalue 0 in this matrix is 2. Okay, it's an eigenvalue of multiplicity 2, but the matrix has only one linearly independent eigenvector. It does not have two linearly independent eigenvectors corresponding to lambda equal to 0. So basically not every n cross n matrix will have a full set of n linearly independent eigenvectors. Okay, so here's another direct consequence of what we just saw. If A in C to the n cross n has n distinct eigenvalues, then A is diagonalizable. This is an immediate consequence because if it has n distinct eigenvalues, then it has n linearly independent eigenvectors. Okay, and so we just saw that result. A has n linearly independent eigenvectors, which implies that A is diagonalizable. Okay, obviously the converse need not hold, that if A is diagonalizable, then it need not have distinct eigenvalues, and I already gave you the identity matrix as an example. Okay, it does not have uh, distinct eigenvalues. All its eigenvalues are equal to 1, but it's of course diagonalizable. Okay, so now we've seen that this similarity matrix that say diagonalizes a matrix need not be unique. So a related question is it possible that there is a single matrix, similarity matrix, that will diagonalize both two different matrices? So we say that A and B are simultaneously diagonalizable if there exists a single matrix S such that S inverse AS and S inverse BS are both diagonal. Okay, what this in words means is that there is a basis in which the representations of both these linear transforms are diagonal. Okay, so both these are diagonal. They need not be the same matrix, the same diagonal matrix. All you need is that S inverse AS and S inverse BS are both diagonal. Okay, in other words, A and B need not be similar to each other, but they can be simultaneously diagonalizable. So here is one result which I won't prove, but it's nonetheless true, is let A and B be n cross n matrices. Okay, and so suppose these two matrices are diagonalizable. Okay, then A and B commute. That means AB equals BA if and only if they are simultaneously diagonalizable. Okay. The proof is not difficult, it's just somewhat long, and so I don't want to do that in class. It basically uses an induction argument on the matrix size to show that they commute if and only if they're simultaneously diagonalizable. Okay, there's one other important result which which we will use quite a lot in this course, and it's also a very useful result. So that is this result. So let A in C to the m by n, now no longer square matrices, and
Hello, sir.
yes,
Sir, what do you mean by A and B will commute even there?
I just said it in words, but
Oh, okay. Okay, sir.
okay,
Yes.
with m less than or equal to n. Okay, then BA has the same eigenvalues as AB, counting multiplicities, together with and additional n minus m eigenvalues equal to 0. Okay, so in another way to say it is that is, if I look at the characteristic polynomial PBA of t, that is equal to t power n minus m PAB of t. So this has n minus m extra zeros because t equal to 0 is a repeated eigenvalue, 0 of this polynomial, with repetition n minus m times. So there are additional n minus m zeros. Of course, the matrix BA, okay, is of size n by n by n, and this is a matrix of size m by m, and m is smaller than n, less than or equal to n, and so this has more number of eigenvalues. It has exactly n minus m additional eigenvalues more on top of whatever are the eigenvalues of AB, but the there are the m eigenvalues of AB will also appear as m eigenvalues of BA, and in addition BA will have n minus m extra eigenvalues which are all going to be equal to 0. And if m equals n and at least one of A or B is non-singular, so they're both square matrices of the same size, then AB is similar to BA. Okay, so this is one example where from this result we see that if I apply this result to the case where m equals n, then AB and BA will have the same eigenvalues, but we've already seen that two matrices could have the same eigenvalues but not be similar to each other. But what this is saying is that if at least one of these two matrices is non-singular, then these two matrices will be similar to each other. Okay, so this is one example where having the same eigenvalues is actually sufficient in for the matrices to be similar, but provided two other conditions are satisfied, namely that uh, m equals n and at least one of A or B is non-singular. Okay, of course, yeah, the thing is we are only comparing, checking whether AB and BA are similar. Okay, so there isn't time to see the proof of this in this class, so we'll see the proof in the next class, which will be Wednesday of next week. That's all for today.